In this video, I want to provide an introduction to the likelihood ratio test, as well as explain some of the intuition behind the formula. So the likelihood ratio statistic is calculated by the following formula. LR is equal to 2 times the log likelihood, which is achieved at the maximum likelihood estimates of that particular parameter. So assume that we're just talking about the univariate case where we only have one parameter which we're varying. So it's equal to 2 times this minus the log likelihood, which is obtained under the null hypothesis being true. And it turns out that asymptotically, if the null hypothesis is true, then this is chi squared with q degrees of freedom under h naught, where q here corresponds to the number of restrictions which we're placing under h naught opposed to the unrestricted maximum likelihood estimation. So in this particular example, q is equal to 1. And the reason that this actually has a distribution under h naught is due to sampling error. Because we don't necessarily pick samples which are exactly indicative of the population, that's why in any given sample, even if the null hypothesis is true, this thing still has a non-zero value. So that's the mathematical formula behind the likelihood ratio test. Let's try and provide some intuition as to why the likelihood ratio test works the way in which it does. So to do that, let's first of all draw some likelihood for a given set of data. So the idea is that on this y-axis, I'm actually going to draw the log likelihood of a data set y, given that we have a parameter theta. So the idea here is that all we're doing is we're varying one particular parameter and seeing how that affects the likelihood. And the likelihood might look something like the mauve line which I've just drawn here. So what we can do is we can think first of all about the level of log likelihood which would be obtained if the null hypothesis is true. So under the null hypothesis, theta takes on a certain value, which I'm going to call theta with a subscript of h naught. And in many practical situations, theta h naught is taken to be 0. Because the idea is that what we're doing is we're testing, often in linear regression or some sort of regression model, is the effect of a particular variable actually different from 0? In other words, does it actually have an effect? And for that particular value of theta, under the null hypothesis being true, there is a corresponding value of log likelihood, which is given by L of h naught here. The idea is that we compare this value of log likelihood with the value of log likelihood which would be obtained if we took the maximum likelihood estimate values. So the idea is that we have a maximum likelihood estimate for the parameter which is given by theta hat maximum likelihood with a star here, and this corresponds to a certain value of log likelihood, and this is the log likelihood essentially under the alternative hypothesis being true. So in this particular example, h1 here is the example where theta is greater than the null hypothesis value of theta. So the idea behind the test is that if there is a significant difference between these two values, perhaps as I've indicated here, then it's very unlikely that the null hypothesis is true, because we can improve our log likelihood, or in other words our likelihood, significantly by transiting from our null hypothesis value of theta to that which is obtained via maximum likelihood. So the idea behind this likelihood ratio test is that if there is a significant difference between these two values, which corresponds to a large value of the term inside the parenthesis here, sort of forgetting about the 2 there, then the likelihood ratio statistic is relatively large. And in that circumstance, because there is a big difference between the log likelihood of h1 and h0, in that circumstance we reject h0. If, however, there isn't significant difference between these two values, so if we were to draw another curve, perhaps we have, for another set of data, a likelihood which looks something like this sort of blue line which I'm drawing here, and for that blue line there is a corresponding value of the value of log likelihood at the maximum likelihood estimate of the parameter, and that's just given by L of h1 primed as I've indicated it here. In other words, there isn't a big difference between the value of likelihood which would be obtained under the maximum likelihood estimates for the parameters compared with the null hypothesis. So in this example, the likelihood ratio statistic would be relatively small, and in that circumstance, we do not reject the null hypothesis. And the idea is that we don't reject the null hypothesis because essentially this difference in likelihood between the value of H0 and H1 could really just be due to sampling error. So we don't, in that circumstance, reject the null hypothesis. Finally, I just want to draw your attention to the reason actually we do reject the null hypothesis if LR is found to be quite large. Chi-squared is a function, especially when you're talking about having relatively low degrees of freedom, which is bunched towards zero. Its probability distribution is bunched relatively towards zero. So if you actually were to obtain a value from that distribution that was very high, it would actually be very unlikely that that would have actually been obtained if that was actually the true distribution. In other words, it's very unlikely that the null hypothesis is true and that the value which you obtained did come from a chi-squared distribution.